are going to start discussing 7.5, which my title is More Trigonometric Equations. What we do is, so there's 3 more versions of trig equations that I want to talk about with you. One of them is when you have identities that you need to substitute so that you can manipulate the equation and solve the equation. And that's usually when I guess the examples we'll see today, there'll be a varying type of trig function. So there might be a sine squared and a cosine to the first. Or there'll be a cosine to the first and a sine squared. Does that kind of make sense? That's an issue. The fact of having 2 trig expressions in the equation is sometimes an issue. I'm not going to say it's 100% of the time an issue, because we did see some in 7.4 where, like this one here, having 2 trig functions in the same equation there in example 7 is okay, because there's a GCF there that I can factor out, and the zero product property takes over, and we're good to go. So that's okay there, but there's going to be some down here, for instance, this one here, that's not okay, because in that one, you can't just start factoring, You might see that, yeah, it's going to be, when I start moving things around, it's going to be quadratic, in nature, but there's no way if I leave that middle term as negative sine theta eventually, there's no way that I can take O and I and multiply them together to get just a negative sine theta. There'll be a cosine kind of wrapped up into that, and that's a problem. So we need to be able to get rid of that. So that's the first kind that we're going to talk about. The second kind will be something kind of like this, where we've got both the same power, but there are no substitutions that are really useful for cosine theta plus 1 and sine theta, because they're both in the first power, right? Our useful substitutions with sine, cosine, and tangent are going to be these things. Those are the ones that we're looking for the most inside equations. Now, I'm not saying these other ones are not useful, and I'm not saying that these other ones with, we'll see some today, not with those, but those could be viable options for substitutions. These we will use today, and those. Maybe I just showed you those. Where's the half angle? There. So we might use those. Those are the ones that are most prevalent in these kind of extra trig equations, or more. I think they're more complex type of trig equations. And then the last one will be something like, and these will be talked about tomorrow, where we've got sine of 2x or cosine of 10x, but that's the argument throughout the entire problem. And we'll talk about how we generate those solutions tomorrow. You might see sine of 2x, sine of 3x, those types of things inside the equations we do today, but it won't be in every single term. So when we get to that example, I'll kind of explain that again and how we decide, do we make a substitution or do we go through the process that we're going to learn tomorrow. So first example here I want to do is 1 plus sine theta equals 2 cosine squared theta. And right away, guys, you recognize hopefully that is quadratic format. So we're going to rewrite this so that everything is equal to 0. I'm going to rewrite this as 2 cosine squared theta minus sine theta minus 1 equals 0. All right, so now the issue, like I said earlier, was the fact that this is cosine and this is sine. There's no way, if you start factoring and say, well, the AC method, I can go, negative 2 and it'd be 2 and negative 1, or sorry, negative 2 and positive 1 would be your 2 things. But then when I start rewriting this, there's no We got 2 cosine squared theta. It'd be minus then 2 sine theta plus 1 sine theta minus 1 equals 0. There is no, other than the 2, there's no common factor that can come out of those front 2, right? So it runs me into a roadblock. Okay, I'm stuck there if I don't make a decision on how to change that. Okay, now I'm going to change the cosine because I have a substitution for cosine squared, right? We do not have a substitution for sine to the first power. Okay, so cosine squared from the Pythagorean identity is this thing, isn't it? Isn't it 1 minus sine squared? We agree with that? That's sine squared theta plus cosine squared theta equals 1. Now if I make that substitution, this becomes 2, and then 1 minus sine squared theta, then minus sine theta minus 1 equals 0. So now 2 minus 2 sine squared theta minus sine theta minus 1 equals 0. And then we've got negative 2 sine squared theta minus sine theta. And now it's positive 2 minus 1, so that's a negative 1, right? No, sorry, positive 1. Positive 1. Equals 0. Okay? We like this to be a positive, right? Can I multiply everything by negative? So multiplying everything by negative gives me that. Now we're going to factor. So we'll take 2 times negative 1, gives me negative 2. And that's going to be then positive 2 and negative 1. That add up to give me this positive 1 here in the middle. Okay? If you're a person that wants to rewrite this as 2u squared plus 1u minus 1, that's fine. Okay? I'm going to kind of skip that right now. I'm just going to rewrite this as 2 sine squared theta plus 2 sine theta minus 1 sine theta minus 1. Can we group these two and group these back two? One come out of the front two. Two sine. That's going to leave you with sine plus 1. And out of the back two, be negative 1, right? So it's going to give me 2 sine theta minus 1 and sine theta plus 1. Zero product property. And we get something like that. Okay, now we got to think about what our solutions are. Because we do all that work, that's a lot of work. But we're judged off what our theta is, right? What we get for the final answer. Okay? So I keep going. So theta, when is theta, for what angle do you get the y value to be a half? Say again? Let's do it in degrees. Okay, so in radians it'd be pi over 6. In degrees that'd be 30 degrees, right? Okay, where else is the y value 1/2? 5 pi over 6. 5 pi over 6. And that is 150 degrees, right? So thinking again, if you need to draw a picture, by all means do so. If we get 30 degrees right there, and that gives me the y value to be 1/2, if I flip that across the y-axis, that y value should still be at a half right there, right? And I got to figure out how many degrees that is. Well, it would be the 180 minus the 30. That reflected. So 150. And then converting back into radians with pi over 6 and 5 pi over 6. When is sine of theta equal to negative 1? 3 pi over 2, 270 degrees. Could I take all of those and add 2 pi k to them? Could I take all of these and add 360k to them? All right. Somebody came to me this morning and asked me, how do I know if it's plus 2 pi k or minus 2 pi k? It doesn't matter because if it's minus 2 pi k and you plug in an integer that's negative, we'll turn it into positive. Yeah. Okay. Ultimately, we use plus 2 pi k most of the time because we're generally used to and asked for solutions that are to the right of the y-axis. But there's nothing wrong with finding solutions that are to the left of the y-axis as well. Okay, so plus 2 pi k or minus 2 pi k is perfectly fine. I don't know if WebAssign will accept minus 2 pi k. But like I said, it's an option. I'm planning on having a test on Friday, so if you were to write minus 2 pi k, I'd give you full credit for that. Okay, so this one here, this is the second type that I want to talk about in which we generate a equation, or we're providing an equation. Now, we only want solutions between 0 and 2 pi, but look at how these relate. Okay, cosine theta plus 1 and sine theta. There's still that issue that one is sine, one is cosine. We want to get rid of that. We want them both to be in the same trig function if possible. Okay? Because right off the bat, if it's not possible, like we saw example 7 from 7.4, we could take out, using a GCF, we could take out one of the trig functions to be fine. Here, there's not a GCF amongst those three terms. So we have to somehow construct the equation, manipulate the equation, so that we do end up with an identity that we can make. Okay? So when I'm talking about sine and cosine, what power of sine and cosine is preferred in making substitutions? Squared, right? We would like to have sine or cosine squared. Well, can't we do that? And do that, won't that allow that to happen? Okay. So we go through and I'm going to get, when I square the left-hand side, it's cosine squared theta, plus then what ends up being 2 cosine theta plus 1 is then equal then to sine squared theta. Okay. At this juncture, you have a choice to either replace cosine squared or sine squared. Okay. Now, one of them is going to produce something that's nice, and one of them is going to produce something that gets us back into the same issue that we started with. Okay, and having two varying trig functions. If I substitute for cosine squared, and it's actually over there on the board, okay, where I've substituted cosine squared with 1 minus sine squared, right? Do you see how doing that, I put that in terms of sine, but now that middle term is still 2 cosine, right? So I'm running through this equation, making substitutions, and it didn't make it any simpler when I made that substitution, right? I'm at the same kind of issue with having that and that being different. Okay, so substituting this one, not the choice. I want to come over here and substitute with that one. What is sine squared the same as? 1 minus cosine squared, right? And now you see that you're left with everything in terms of cosine of 1 theta. The benefit of that, guys, or I guess maybe not the benefit, maybe it's a bad word. I guess the process that I'm going through in my mind when I look at that is thinking, when I do substitutions, I want to be lazy about it. Okay? Physically, maybe it's more mentally challenging, but I want to be physically lazy. I don't want to do a whole lot of substitutions. Okay? So I'm going to look for the object that's kind of least multitude up there. Okay? Sine only shows up once up there, right? Cosine shows up twice. So in being lazy, I'd like to substitute just sine. Okay? Instead of having to deal with the cosine twice. Does that make sense, everybody? Okay? So that's maybe something to think about as you're going through these to help you decide what to do. Okay? So I see this kind of thing. I see two cosines written out and one sine written out. That's kind of an identifier for me to address this one. Okay. So now we're just going to set this up equal to 0. So add cosine squared to both sides. And then subtract 1 from both sides. So the 1's cancel out. That was really nice. So what happens here then, think about what this is. This is like a 2x squared plus 2x equals 0. What would you factor out of this? 2x. So what are you going to factor out of this? 2 cosine. So this turns it into a GCF factoring problem. Take out my 2 cosine, leaves you just cosine plus 1, right? So this is going to give me 2 cosine theta equals 0. Cosine theta plus 1 equals 0. Divide both sides by 2, so it gives me cosine theta equals 0. This gives me cosine theta equal negative 1. So if cosine, let's do this in degrees first. If cosine theta is equal to 0, at what degree is cosine 0? 90 and 270. At what degree is cosine negative 1? 180. So then 90 is pi over 2. 270 is 3 pi over 2. 180 is pi. And the reason I do that is because look at the answer. I wanted it between 0 and 2 pi, right? So solutions for theta, pi over 2, 3 pi over 2, pi. Now if they wanted to go from 0 to infinity, or sorry, negative infinity, positive infinity, so they would write this as the interval, then you would 2 pi k that stuff, right? Add 2 pi k. The reason in that interval 0 to 2 pi that they put the parenthesis around 2 pi is because if 2 pi is an answer, 0 would have also been an answer. Does that make sense? So you would already have, so they don't want redundant solutions inside that interval. It's not really a big deal, but that's the reason one of them's closed off and one of them's open. Okay, they don't want that. They don't. If you include 0, they don't want you to include 2 pi. Is that all right? Okay, so that's an example of having to square things. Now let's take a look at this, because algebraically, guys, and actually maybe we do this. Let's remember algebraically, whenever we square an equation, we can create extraneous solutions. We just squared an equation. There could be extraneous solutions here. So let's go see if these things create problems or not. If I plug in pi over 2, so I have cosine of pi over 2 plus 1 equals sine of pi over 2. What's cosine of pi over 2? 0, right? Is 0 plus 1 equal, what's the sine of pi over 2? 1. Does 1 plus 0 equal 1? So pi over 2 works. If I try 3 pi over 2, cosine of 3 pi over 2, cosine of 3 pi over 2 is 0, right? Plus 1 equals, what's the sine of 3 pi over 2? -1. What's that tell me? There's an issue there, right? That one's not, that's an extraneous solution. Okay? If I try pi, what's cosine of pi? Cosine of pi is -1 plus 1. Sine of pi is 0. Okay? So there we see that pi or 2 and pi are really our only solutions. If we were to graph this, the cosine of x plus 1 and sine of x. Okay? If we look at x equals pi over 2, x equals pi. If I look at 3 pi over 2, notice how that's not a solution, even though the algebra told it was, right? Okay, so that's the thing that we got to pay attention to. In that version of an equation where we square both sides, all the time when you square things, you potentially incorporate extraneous solutions. Okay, and that problem is not going to it's not going to identify that extraneous solution until you substitute back in. Okay, so always be on the lookout for that. That's that one additive step that a lot of people forget about. Okay, so those are the only questions I had in the PowerPoint or the document here. Let's grab a couple from the textbook. All right, tomorrow I want to talk about questions like this that look like 2 sine of 3 theta, maybe plus sine of 3 theta, to where when we go through and we look at all of the arguments, they're all 3 thetas. Does that make sense? Okay. Even if I just have, something like this, it's still all arguments are 3 theta. The next example I want to do is something like this, where it's sine of 2 theta minus cosine of 1 theta. Now the arguments differ, right? When the arguments differ like this, you want to think about making either double angle or half angle substitutions. And there's nothing out of the question saying that, that couldn't be a sine of 3 theta and a cosine of 1 theta. And if it's sine of 3 theta, then you have to use your sum and difference formulas for sine or cosine. Most of the time we'll stay away from those, but it's an option. Okay? It's a type of equation. A lot of times I've seen people come back when I did not teach this as a course through rows. People would go on to OSU or Toledo or wherever, they come back and ask me, how do I do sine of 3 theta essentially equals cosine of theta? Well, the way you do that is that you have to change sine of 3 theta into sine of 2 theta plus theta and use your sum and difference rules. We might see 1, 2 of those maybe tomorrow. But normally speaking, when we see questions like this, we're going to want to use a double angle substitution. Okay? Does anybody remember what the sine of 2 theta, what that substitution looks like? Okay, so sine of 2 theta turns into 2 sine theta cosine theta. 2 sine theta cosine theta. Now when I make that substitution, this ends up being a really nice problem because what do you see happening between that term and that term? They have a what in them? Yeah, they have a GCF of cosine. So let's factor that out. I factor out cosine theta, it leaves me with 2 sine theta minus 1 equal to 0. Zero product property says cosine theta is equal to 0. 2 sine theta minus 1 is equal to 0. Sine theta is a half. Cosine theta is 0. Where is cosine equal to 0? $90 and $270. Where is sine equal to a half? $30 and $150. And if we go radian, 3 pi over 2, 3 pi over 2, pi over 6, 5 pi over 6. And you can plus 2 pi k plus 2 pi k. You are seeing, or you might, I don't know if you've seen it yet, you might see in WebAssign that they, let me double check, see if the textbook does this. Maybe WebAssign doesn't do this, but I would be okay with this, guys. If you were to want to write, because on your test, I'm going to have questions like this, and you know, a lot of people aren't going to want to write pi over 2 plus 2 pi k, and then 3 pi over 2 plus 2 pi k. It becomes tedious. So if you just want to write pi over 2, comma, 3 pi over 2, comma, pi over 6, comma, 5 pi over 6, put those in parentheses, and then put plus 2 pi k, I'm 100% okay with that. Okay? Notation-wise, maybe those parentheses should be braces, but I don't really care. Just show me that you know all of those need 2 pi k added to them to get the infinite solutions. And it saves you a little bit of writing. The same thing if we're working in degrees. Just don't add 2 pi k, add 360k. Is that all right? Okay. What if we did something like this? Let's go cosine 2 theta equals 3 sine theta minus 1. What's the issue with this equation that we have to make a substitution before we go on? What jumps off the page here? The sine and the cosine are a problem. But the bigger problem is that they're 2 theta and 1 theta. Okay? The reason that's a bigger problem is because if I address that first, the other problem probably disappears. Okay? The fact that they're differing in sine and cosine. So let's address the cosine 2 theta. Let's take that thing, and if we come to the side, hopefully we remember our cosine double angle formulas. There were 3 of them. There was cosine squared theta minus sine squared theta, and then the other ones we got by substituting cosine squared with 1 minus sine squared. Okay, and that turns into 1 minus 2 sine squared theta, and the other one was taking sine squared to replace it with 1 minus cosine squared, and that turns into 2 cosine squared theta plus 1. Those are your 3 versions of the cosine double angle, right? Now, I can choose any one of those. But if I choose that one, I'm going to have to make another substitution inside my equation. If I choose that one, I'm going to have to make another substitution inside my equation. If I choose that one, are all my terms going to be in terms of sine? Yeah. So I'll have 1 minus 2 sine squared theta equals 3 sine theta minus 1. If I were to choose either of these with the check mark next to them, my next substitution would be exactly what we substituted in this section when we dealt with the cosine double angle, that we substituted cosine squared with 1 minus sine squared. Okay, so there's nothing wrong with doing any one of those three. It's just that the top and bottom one are going to be a little bit longer for you to solve. Okay, one more substitution. With this, then, we can start to get everything equal to 0. So I'll make the left-hand side 0 here. I'll add 2 sine squared to both sides. It'll be plus 3 sine theta, and then minus 2. Why don't you guys take a minute on your own and see if you can end up factoring that, and then we'll come back together and see what matches up. All right, so if we factor through there, we get down to 0 equals 2 sine theta minus 1, and 0 equals sine theta plus 2. Solving both those then, sine theta equals a half, sine theta equals negative 2. When does sine theta equal a half? 30, 150, right? When does sine of theta equal negative 2? Never. Okay? And that's, I think something that we want to happen in our equations because it eliminates a little bit of the work that we have to go through. So 30 and 150, if we were to graph these guys, that's always a good idea. Kind of see what is really going on. Remember, cosine 2 theta is going to take our cosine function and squeeze it down, right? Okay. So that's that one. And then the other one was 3 sine minus 1. So 3 sine of x minus 1. Okay. And if I look at that between 0 and 2 pi, okay, how many times do those two curves intersect? Just one. Or sorry, just twice, right? At pi over 6. And then again at 5 pi over 6. So that confirms our solutions, right? Okay. I want to do one more. Let's see here. Let's go. Let's say tangent squared theta minus 2 secant theta is equal to 2. Remember, if we took sine squared theta plus cosine squared theta equals 1, and we divide everything through by, first one divide everything through by sine squared, and then the second one divide everything through by cosine squared, right? Okay. And that's the reason I don't try to memorize those two, because I mess up. For some reason I mess up the cosecant and secant, which one goes with cotangent, which one goes with tangent. So I don't try to memorize them. I just know that I can develop them through division real fast. Okay. And now, the reason I do that, or I knew that, is because I knew there was something out there, some identity that we talked about in the past, that paired up secant and tangent, right? Okay. So I want to bring that to light and look at that one and see if can I make a substitution here that will produce an equation that is just one of these trig functions. Okay. Now, if I look at this, which substitution makes more sense? Tangent squared or secant to the first? Tangent squared. Tangent squared is going to be the same thing as secant squared minus 1, right? Minus then 2 secant theta. I'm just going to move this 2 over as minus 2. And now we've got something that we can deal with. Secant squared theta minus 2 secant theta minus 3 is equal to 0, right? Can we factor that thing? Yeah, this is an easy factoring. So this is, this is like x squared minus 2x minus 3, right? So that's going to factor to secant theta minus 3 and secant theta plus 1. So then secant theta minus 3 is equal to 0. Secant theta plus 1 is equal to 0. So secant of theta is equal to 3. And secant of theta is equal to negative 1, right? Now, are those things that you know off the unit circle? No. Okay? This is probably the one time we know we're allowed to do this. Maybe working with proportions, this benefited us sometimes. But this is the one time where you can take the reciprocal of one side of your equation and then take the reciprocal of your other side of your equation, and it actually proves to be something beneficial. Because if I take the reciprocal of this, what do I get? 1 over secant, which is the same thing as cosine, right? Okay? But if I take the reciprocal of the left-hand side, I got to take the reciprocal of the right-hand side, right? So it gives me 1/3. Same thing over here. Cosine theta, reciprocal of negative 1, still negative 1. That might be one of the few instances in regards to taking the reciprocal of both sides of an equation, and it generates something that is productive, something that is useful for us. Okay. Now, this one's obviously an ugly one, but when is cosine equal to negative 1? At what degree? (180), right? Okay. If I'm in radians, it would be pi, correct? Okay, so let's now take the cosine theta equals 1/3 and mess around with that one. So if we arc cosine of 1/3, okay, it gives me 70.528 degrees, right? Okay, so that's one of our solutions for cosine being 1/3, 70 degrees. But isn't there one down here as well? So that would be 70 degrees down there. But how do I get that angle right there? That's the theta we're interested in. Right, so 360 minus previous answer, 289.471, right? So those are my two answers. In degrees, theta equals 70.528 and theta equals 289.471. Now what I could do, if I wanted it in radians, I could take that number and multiply by pi over 180, 1.23 radians. Okay. I can then also take this number and multiply that by pi over 180 and get that amount of radians. Is that okay with everybody? Okay. If this is that 70 degrees, this is just an alternative way of doing it. Let me highlight the equal sign. If that's 180, or sorry, if that's the 70 degrees, in finding that 5.05 number, could I have also taken 2 pi minus that? Is that going to make sense? Okay. Now they do differ a little bit. It goes 0.52225.8, and then this one's 7.9. This one just gives me a 9 there. That's the rounding error aspect of things, right? Okay. So you can find if the task is to find things in radians, I suggest finding them in degrees first, and then convert over into radians. Okay. More often than not, the people that miss questions like this when they ask to write your answers in radians is that they put 1.23 and then they put pi on the end of it. They take 5.05 and put pi on the end of it because they think just every time I do radians, it should have pi in it. You're right, it does. But in these cases, that pi has already been multiplied through. Okay. The other thing I see is that they're uncertain, so I just put a degree symbol with those numbers. Okay. So just be careful that we understand. I think the same thing. Do everything in degrees. Do every answer in degrees, and then if the directions say change to radians or write our answer in radians, then you manipulate them by that conversion factor. I've opened up 7.5. I'm planning on. I think I got that set to be due on Thursday. Tomorrow we'll wrap up 7.5. Talking about those multiple angle questions, and then at some point, maybe tomorrow, get you kind of a practice test out. I do want to have a test on chapter 7 on Friday, and then I'll get us into chapter 8. We'll spend a couple weeks on chapter 8, and I'll get us into chapter 9. Spend a couple weeks on chapter 9. Seniors are out the 17th. Is that right? Okay, so we will have our final then on the 16th and 17th. And then seniors, you will be back at the bottom of the food chain.